Hey guys, good morning. Um, so bear with me. This one's going to be a little bit longer video, um, and I do hope you guys watch this one because this lesson can be a little tricky. This is one that we probably would spend an extensive amount of class time with our notes getting through this. Uh, but first, looks like we will be doing online schooling for the rest of the year. For you guys take the test the second week of May. So I guess technically, and I can't say anything about what it's going to look like after you guys take the test, but I imagine that at that point the AP class would be done at that point in that second week of May. We have a BLT meeting on Thursday. We'll probably find out a little bit more information then, and I can relay that to you guys. So today, integration of composite functions. So we are looking at basically how do you integrate composite functions. So the first thing, if I think about composite functions, I have one function really inside another function. So if we think about that, that's really talking about the chain rule. Is where that really shows up. And we got some examples here on this page. Sine of 3x. 3x is contained within sine. E to the cosine of x. Cosine of x is showing up in the exponent with e. This one down here, x squared plus 3, it's the inner part of that natural log. So composite function. So let's kind of walk you through this page here. The first thing is if I took the derivative of sine of 3x, took the derivative of e of cosine of x, took the derivative of the natural log of x squared plus 3, these all kind of have unique rules and some things that we would have to do to actually find the derivative. Now, if I look at sine of 3x, the first thing I would have to do is, what is the derivative of sine? It is cosine. So I have cosine of 3x, but then I have to apply the chain rule. So then I would have to take what is the derivative of 3x, and that's 3. So the derivative of sine of 3x ends up being 3 cosine of 3x. Now here's where it gets a little interesting. So if I go here to, all right, let's say I would take the integral of 3 cosine of 3x. So what is the antiderivative of 3 cosine of 3x? This is where we have to start really picking out patterns in knowing that, hey, the derivative of 3x right here shows up right there in front as 3. Down here in the second one, e the cosine of x. If I were going to take the derivative of that, now I'd have e cosine of x times the derivative of the exponent. So the derivative of cosine is negative sine of x. So there is our derivative of that function. So I know if I take the antiderivative of this function, I should get what I started with. So if I'm looking here, it says the integral of negative sine of e of cosine of x. So I know, all right, here's cosine of x, the inner part of that function. The derivative of that is showing up next to it. That's the chain rule, kind of working backwards. So I know if I took the antiderivative of this, I should get that. This last example down here, let me erase a couple of things. The natural log, I know that if I take the natural log of a function, the derivative of that is going to be the derivative of the inside of the natural log over the what's inside of the natural log. U prime over u. I guess we could refer to that as that as well. There we go. So if I had, the integral of 2x over x squared plus 3, I noticed that 2x is the derivative of the bottom, which is the kind of working backwards from the natural log. And I have put the absolute value in there because I know that we cannot be taking the natural log or a log of a negative number. So it's still going to have to be positive. So I need to make sure I just put absolute value bars in there just to say that it's going to be positive. And then this last one here, A little bit more complicated. I have x squared plus 3 to the 1/2 power. That's my original function. So if I were to take the derivative of that, I would have to take the 1/2, bring it down in front, which is what we're doing right here. Subtract 1/2 by 1, I get negative 1/2. But then I have to multiply using the chain rule, the derivative of x squared plus 3, which is 2x. So I know that the 2 and the 1/2 are going to cancel, and we end up with this right here. So you're going to have to be able to recognize, like, all right, well, I have basically the derivative of this inside function showing up somewhere else. And I can write, 2 over 2. That's by far the hardest one. So with this, what we are going to be doing is really taking the antiderivative of composite functions. The first way that we're going to look at it as, all right, do we have the derivative of the inside part of a function showing up in the integrand? If you do, that gives you the license to integrate. Okay? Do we have the derivative of the inner part of your function showing up? If you do, then we can go ahead and basically use the chain rule and work backwards. And I know that, all right, if I just take the antiderivative of f prime, I'm going to have f, and then we'll have g of x, and then plus c. So that's the main thing, is do you have the derivative of the inside part of your function showing up in your integrand? So we're going to look at 8 examples here. Some of them we do. Some of them we're going to have to do a little bit of work to get there. So this first one, the integral of 3 cosine of 3x. So cosine of 3x is kind of like the main part of our function. That's why it's highlighted it in green. So the inner part of that is 3x. Do you have the derivative of 3x showing up somewhere else? Yes. The 3 is out front. So I can go ahead and just think, what is the antiderivative of cosine? It is sine. So my answer is sine of 3x plus c. This next example, we really have, if I were to rewrite this, instead of the cube root, I'm going to write it as x squared plus 5 to the 1/3 power. So do I have the derivative of the inside showing up in the integrand? So the derivative of x squared plus 5 is just 2x. So yes, we do. Okay, so now I'm just thinking, working backwards using the chain rule. So what is the antiderivative of this? X to the 1/3 power. I'd have to add 1. So I'd have x squared plus 5 to the 4/3 power. And then I'm going to divide it by my new power. So dividing it by 4/3 is the same thing as multiplying by 3/4. And we have plus c. There's my derivative. This next example, the integral of 2 sine of 2x plus 3. So the sine part is really the main part of this function. So if I look at the inside of that, is the derivative of 2x plus 3 showing up in your integrand? The derivative of 2x plus 3 is just 2. Yes, it is. It's showing up. So the antiderivative of sine is negative cosine, and then the inside part stays the same. Next example, the integral of 2x plus 2 over x squared plus 2x. You should be able to notice that the derivative of the denominator is in the numerator. The derivative of x squared plus 2x is 2x plus 2. So there it is in the numerator. Anytime that you have the derivative of the denominator in the numerator like this, this is the natural log. So the antiderivative of this is the natural log of x squared plus 2x. With all of these 4 so far too, once you have your final answer, you should be able to take the derivative of this final answer and get that integrand. So I know that the derivative of sine of 3x plus c is 3 cosine of 3x. And I know that the derivative of this would give me this up here. The derivative of natural log of x squared plus 2x is 2x plus 2 over x squared plus 2x. So those should be holding true the entire time. All right, these last 4 are a little bit unique. Cosine of 3x plus 2. So if I think there, do I have the derivative of 3x plus 2 showing up in the integrand? No, I don't, because it's just cosine. So what I'm going to do is I'm basically going to write in my derivative of 3x plus 2. So the derivative of 3x plus 2 is 3. So I'm just going to literally write in 3. Now, the problem is you can't just add numbers into an equation or into a problem, but we can add the number 1 because multiplying by 1 is an identity. So we're still left with exactly the same thing. We're just kind of changing the look of it. So if I put a 3 in the inside part of my function, I also need to put a 1/3 on the outside part of my integral because 1/3 times 3 is 1. At this point, we are going to take the antiderivative of this. So I know the antiderivative of cosine is sine. So there's my antiderivative of the inside part of that function. And I just bring the 1/3 and just carry it down. A little bit tricky there. So this next one, I have the integral of 3x times x squared plus 2 to the 1/2 power. So do I have the derivative of x squared plus 2 showing up in my integrand? The derivative of x squared plus 2 is 2x. I have 3x. I need it to be 2x. So what I can do is I can take the 3, I'm going to move it out front, and then we're going to basically do the same thing we did on the last problem. I need a 2 to show up right here. So I'm going to put a 2 in front of our x, which means I also need to put a 1/2 out front because 1/2 times 2 is 1, and I'm allowed to add 1. 1/2 times 3 out front is 3/2. So now I take the derivative or antiderivative of the inside part. So I'm really just looking at this right here and think of it as to the 1/2 power. I need to add 1, divide by my new power. So I end up with x squared plus 2 to the 3/2 power. Dividing by 3/2 is the same thing as multiplying by 2/3, which is right here. And then I just bring the 3/2 down out front, and I'm going to multiply the 3/2 and 2/3, just kind of clean it up to make it a little bit nicer. And I end up with this as my answer. All right, let me do some erasing. So that way I can scroll down a little bit. All right, so the integral of 5e to the 3x power with respect to x. So now e to the 3x, so the derivative of 3x would be 3. That's not showing up in my integrand, so I need to take the 5, same thing I did on the last one, and take it out front, which is right here. So now I'm going to add the 3 in front of our exponential expression, which means I need to add 1/3 out front since 1/3 times 3 is 1. So then I just go, all right, what's the antiderivative of e to the 3x? It's e to the 3x. And then I just bring down to 5/3. This last one here, first thing is rewrite it in standard polynomial form, or it's not standard polynomial form, but I'm going to basically take this square root and move it up top with the 3x. So I have 3x times 2x squared plus 3 to the negative 1/2 power. So the the derivative of 2x squared is 4x. Well, I have 3x. So I really don't want that 3 to be there. I need it to be 4. So I'm going to take the 3, move it out front, put a 4 in its place, which means I need to add 1/4 out front. Now from here, I'm going to take the antiderivative of the inside. So I'm really just looking at this part of it. The antiderivative of this, I would have to add 1 to negative 1/2, which is 1/2. And then I need to divide it by my new power. So dividing by 1/2 is the same thing as multiplying by 2. And then I just cleaned it up. 3/4 times 2 is 3/2. And there is my antiderivative. All right. So there's 8 examples there of really where we can just go ahead and integrate. We had a couple of problems where I had to do a little bit of work. So that way we had kind of that license to integrate. We had the derivative of the inner part of your function showing up in your integrand as well, which then we can go ahead and just go from there. Now, looking at this example, Now I have the integral of x times 2x minus 1 to the third power. So the inside part of that function is 2x minus 1. The derivative of that is 2. Okay, the derivative of that is 2. Is that part of the integrand? No, it's not. Is it attainable by multiplying the integrand by a constant? No, because there's no way that I can multiply x by a constant to get it to equal 2. No, 2 over x is not a constant. So in this case, when this happens, we're going to have to find the antiderivative in a different manner. And the way that we are going to look at is u substitution. Okay, so u substitution has a couple of rules. Okay, has a couple of rules, and it's a little bit unique. First thing, we're going to let u equal the inner function. So in this case, my inner function is 2x minus 1. I just write u equals 2x minus 1. We're going to find du and solve the equation for dx. Basically, what we're going to have is I have my original function over here, or the original integrand, the integral of x, the 2x minus 1 to the third power to the with respect to x. I'm going to basically replace all of these x's with u's. And it's going to be a little bit different. So I'm going to now take my equation right here. Let me go down to this. Find an expression for x. Or I guess I can just go ahead and take the derivative of this right here. So the derivative of this, the derivative of u would be 1 du, because I took the derivative with respect to u in this case. And then over here on the right-hand side, the derivative of 2x minus 1 would be 2, and then with respect to x, because that's what I took the derivative of with respect to x. So we have du is equal to 2 dx. So I want to solve this equation really for dx. I'm going to divide both sides by 2. 1 divided by 2 is 1/2. So we have dx is equal to 1/2 du. That's nice. This is going to sit there for a second. Then the last thing that I need to do is find an expression for x in terms of u. So I'm going to go back, working really with this inner function again, and I'm going to rewrite that inner function in terms of u. So add 1 to both sides, divide by 2, we get u plus 1 over 2. So now I have an expression for x, and I have an expression for d of x, or dx, and we have an expression for really this inner function. So now I'm going to do a little bit of rewriting, and this is where the u substitution part comes in. Here, x. I have something that represents x using u. X is equal to u plus 1 over 2. I have this, my inner function represents 2x minus 1. That's equal to u, so I'm just going to put u in its place. dx is equal to 1/2 du. We have an expression for that. From here, I'm going to take this and kind of just clean it up a little bit. So instead of having it written like that, I'm just going to kind of multiply everything out. So I have 1/2 u plus 1 times u cubed times 1/2. Let's see here. I would have, 1/2 times 1/2 is 1/4. So I can take the 1/4 and just write it outside. There it is. So then I would take u cubed and just distribute. So I end up with u to the 4th plus u cubed. So if I look at this expression right here, 1/4, which doesn't, it does matter, but just sitting out front. But the integral of u to the 4th plus u cubed du. Could we integrate that using our basic integration rules? Yes, we could. Add 1 to 4, that's 5, divide by my new power. Plus, add 1 to 3, divide by my new power is 4, plus c. Now I'm going to take the 1/4 and distribute it to, I would say all three terms, but saying 1/4 times c is still going to just give you a constant. So we end up with 1/20th u to the 5th plus 1/16 u to the fourth plus c. Then the last thing that I'm going to do is take out u and plug back in 2x plus 1. So here, right, is my final answer. 1/20th, 2x minus 1 to the fifth power plus 1/16th, 2x minus 1 to the fourth power. That right there is u substitution. So the idea is, with that inner function, if you take the derivative of that, is there a way to rewrite the rest of your integrand so that way it shows up as the derivative of your integrand? In this case, we could not, so I'd have to use u substitution. So the 3 steps with substitutions or u substitution is I really need to have an expression that represents x, I need to have an expression that represents u, and I need to have an expression that represents dx. And that's kind of all of the steps there. And to be honest here, this is probably the most difficult thing that we've done so far this year. So we're looking at another example here. I have the integral of 2x plus 1 over the square root of x plus 4, just rewriting it. We have 2x plus 1 times x plus 4 to the negative 1/2 power. So if I were to take the derivative of x plus 4, I would get 1. Is there a way to rewrite 2x plus 1 so that way it's just 1? No, there's not. Using a constant, there's not. The only way I would do that is if I divided 2x plus 1 by 2x plus 1, which, that's not a constant. So kind of going through our steps here. First thing is I need to let u equal the inner function, which is my x plus 4. So u is equal to x plus 4. Now, the second part is take the derivative of that statement. The derivative of u is 1 du. The derivative of x plus 4 is 1 dx. So in this case, now I would solve this equation. 1 du is equal to 1 dx, 4 dx. So divide both sides by 1. Dx is equal to du. That's nice. And then the third thing I would need to do is I need to find an expression for x in terms of u. So I can take that beginning inner function, u equals x plus 4, basically subtract 4 from both sides, and now I know that x is equal to u minus 4. So now I'm going to go back here to the very beginning. Here's what I have initially. Now I'm going to substitute out all of those expressions for some stuff that I just found. So, it's windy outside. So instead of 2x plus 1, I'm going to take out x and I'm going to write in the expression that represents x, which is u minus 4. Instead of x plus 4, that was my inner function, I'm going to write u. So I have u to the negative 1/2 power. Instead of dx, I'm going to plug in what's equal to dx. In this case, it's just du. So now I'm left with an integrand and a problem that's all in terms of u. So I'm going to now rewrite this in standard polynomial form. So I'll distribute the 2. 2u minus 8 plus 1 would give you 2u minus 7. And then I have u to the negative 1/2 du. Distribute the u to the negative 1/2 to the 2u minus 7. And I would have 2u to the 1/2 power, since u to the first times u to the negative 1/2 is u to the 1/2, minus 7u to the negative 1/2 du. Now I'm just going to integrate. The antiderivative of 2u to the 1/2 power is 2u to the 3/2 power divided by 3/2. Cleaning that up, 2 divided by 3/2 is 4/3. So I have 4/3 u to the 3/2 power minus antiderivative of 7u to the negative 1/2 would be 7u to the 1/2 power divided by my new power, 1/2. And I get minus 14u to the 1/2. Now the last part plus c, the last thing we need to do is take out u and put back in our expression that represents that in terms of x, which is x plus 4. And there is our antiderivative. And I will say, I know this is going to be a little bit difficult of a lesson, But I did include the answer key to the homework on here right off the bat, because I know that you guys are probably going to have questions going through the homework. And just use that as a reference guide to make sure that you're getting the correct answers. And if you have any questions about anything, kind of just reach out. All right, so in this last one, we're finding the value of the integral from 0 to 4 of x times the square root of 2x plus 1 dx. Now, here's the nice thing about this in thinking about the AP exam. This problem right here, do we technically need to know how to do all of this stuff? No, because since you're taking this test at home, I imagine you're going to have the use of a calculator at all times, because how are they supposed to know whether you have a calculator or not? So if this were a problem on the test, I would literally just type this into my calculator and get my answer. And that would be the easiest thing to do. Using your graphing calculators, and we'll have to figure out a way. I'm gonna have to get you guys those calculators and really make sure that they're charged and ready to go before May 11th, which I don't really know how I'm going to do that yet. So that's something I'm going to have to think through between now and then. But if this were the case, if this were a problem, I would just type it in and you would get the answer. Otherwise, if we're going to do this by hand, I would have to say my inner function is 2x plus 1. So u is equal to 2x plus 1. I would take the derivative of both sides and then isolate and get dx by itself. Then I would also need an expression in terms of x. So I'm going to take u minus 1 is equal to 2x. Divide both sides by 2. So there's an expression that represents x, and I'm going to substitute everything in. But like I said, the nice thing is, you're going to have a calculator for these problems. So this one shouldn't really be an issue, because it's just going to be a matter of just plugging into your calculator and actually getting your correct answer. All right, so look at the homework. Let's say today's Tuesday. I'll give you guys Tuesday and Wednesday to look at this homework. On Thursday of this week, I'm going to post another lesson. So kind of the main idea here is I want to post the lesson on Thursday. You guys can then look at that technically Thursday, Friday, Saturday, Sunday. Coming back next week, I will post something on Monday, and we'll have that for Monday and Tuesday. And then basically that is all of our new content that we needed to learn. And then from that, we're going to have a little bit of time really to review and go back and look at other topics. And we'll talk about that next week. So take a look at this homework. If you have questions, just make sure you email me. Sorry for the long video. Just a lot of content in there that we had to talk about. So like I said before, hope you guys are doing well. I miss you guys. This all just flat out sucks. I'm going to be being honest with you. But if you have questions, just reach out to me. Hope you guys are doing well.